There are cases where a system of linear inequalities can have no solution, meaning there's no shared region with points containing points that satisfy both inequality statements. And we'll look at an example of that in this case. Taking inequality 1, rewriting it as an equation, and solving for y will give us y is equal to 4x plus 4. For inequality 2, we'll end up with y is equal to 4x minus 8. Notice again that we have the same slope, but different y-intercepts. So we'll have the graph of two parallel lines. Looking first at equation 2, we have an intercept at -8. We'll go up 4 and over 1, up 4 and over 1, to come up with the slope of that line. For equation 1, we'll have our intercept at +4 and still a slope of 4. We can also apply that slope in the opposite direction by going down 4 and to the left 1. And again, with more accurately drawn lines, we would have two parallel lines that would never cross over with one another. We can use 0, 0 as a test point. We could look at using 3, 0. And we could look at -2, 0. We won't go through the process of verifying that this doesn't work in each case, but we would take 0, 0, plug those into both inequality statements, and do the same for the other pairs. And what we would actually see is that none of these three pairs make both inequality statements true. What would actually happen if we were to graph these as separate inequalities is for inequality 1, we would be shading everything sort of to the left or above this line. And for inequality 2, we'd be shading everything to the right or below this line. But what we're looking for with a system of linear inequalities is where those regions overlap, points that make both inequality statements simultaneously true. So in this case, we would represent our solution, or lack of a solution, as simply an empty graph, because there is no region where these two inequality statements overlap. So again, we could respond by either saying there is no solution or presenting our solution as just a blank graph.